welcome back. In this video, we're going to look at blinding in an experiment and the placebo effect. So both experiments and surveys, we know, use randomization, but they do so in different ways and for different purposes. Sample surveys try to estimate population parameters. So the sample needs to be as representative of the population as possible. By contrast, experiments try to assess the effects of the treatments. Please note that experiments are rarely performed on random samples from a population. So please don't describe the subjects in an experiment as a random sample unless they really are. More likely, the randomization was in assigning the subjects to the treatments. Experiments can draw stronger conclusions than observational studies. Only by actively manipulating the factors can an experimenter conclude the observed changes are due to the factors themselves. This is the fundamental insight of the scientific method. Experiments involve treatments, and the treatments, remember, are made up of factors and levels. And to fully understand the effect of a treatment, you have to have something to compare it to. Such a baseline measurement is called a control treatment. And the experimental units or subjects to whom it is applied are called a control group. In an experiment, we use a control treatment as another type of level of the factor in order to compare the treatment results to a situation in which nothing is done. When we know what treatment was assigned, it's difficult not to let that judgment influence assessment of the response, even when we try to be careful. To avoid this problem, it would be better to disguise the treatment as much as possible. We call this strategy blinding. And we blind the participants to the treatment. Okay, so, and also you can blind the experimenters. There are two main classes of individuals who can affect the outcome of the experiment. Those who could influence the results, so the subjects, the treatment administrators, or the technicians, and those who evaluate the results. Judges, treating physicians, etc. When all the individuals in either of these cases are blinded, an experiment is said to be single blind. When everyone in both classes is blinded, we call the experiment double blind. So double blind is when the participants and the experimenter don't know the treatments. Please pause the video and try to answer the question. In our experiment to see if the new pet food is now safe, we're feeding one group of dogs the new food and another group of food we know to be safe. Our response variable is the health of the animals as assessed by a veterinarian. Should the vet be blinded? Why or why not? And how would you do this? Can this experiment be double blind? And would that mean that the test animals wouldn't know what they were eating? So typically, whenever the response variable involves judgment, it's a good idea to blind the evaluator to the treatments. The vet shouldn't be told which dogs ate which food. And yes, there is a need for the experiment to be double blinded, right? Workers who are maybe caring for the dogs, they should not be aware of which dogs are receiving which food because, they could have maybe a liking towards one dog over the other and switch the treatment, and that would mess up the response. So we'll try to summarize that here. Whenever the response variable involves judgment, it's a good idea to blind the evaluator so they don't know which patients are getting which treatments. And then, yes, there is a need for the experiment to be double-blinded. And as we said, the reason for that is so that those who are giving the food to the dogs don't know which treatment as well. And that's just so that they don't bias anything or, have a favorite dog. Often simply applying any treatment can induce improvement, and such improvement seen with a treatment, even an effective treatment, can be due simply to the act of treating. To separate these two effects, we can use a control treatment that mimics the treatment itself. A fake treatment that looks just like the treatments being tested is called a placebo. And think of placebos as like sugar pills sometimes. So it's a pill that looks like the pill that is actually going to, they're looking to see if that it actually helps, but it's doing nothing. These are the best way to blind subjects from knowing whether they're receiving the treatment or not. The fact is that sometimes subjects treated with a placebo sometimes improve. This is called the placebo effect. And it highlights both the importance of effective blinding and the importance of comparing treatments with a control. In summary, the best experiments are usually randomized, double-blind, when we can make them that way, comparative, we always want to be able to compare groups, and placebo-controlled. Recall the tomato problem. Suppose we had wanted to use 24 tomato plants of the same variety for our experiment, but the garden store had only 12 plants left. Then we drove down to the nursery and found just 6 more plants of that variety. Using only 18 plants is okay, but we worry that the tomato plants from the 2 stores are different somehow or have received different care. How can we design the experiment so that the differences between the stores don't mess up our attempts to see the differences among the fertilizers? So when groups of the experimental units are similar, but not the same, it's often a good idea to gather them together into what we call blocks. Okay? And by blocking, we isolate variability attributable to the differences between the blocks so that we can see the differences caused by the treatments. In a completely randomized design, each of the 18 plants would have an equal chance to land in each of the 3 treatment groups. The randomization is introduced when we randomly assign treatments within each block. Because randomization occurs only within the blocks, plants from one store cannot be assigned to treatment groups for the other. We call this a randomized block. So here's an example, okay? So you can see the design here. You've got your 12 tomatoes from, we'll call it store A, and then 6 from store B. And what we do is we create these blocks. So block A will contain just the 12 tomato plants from store A. Block B will contain just the 6 plants from store B. And then we assign the 3 treatment groups to the plants in block A and the 3 treatment groups to the plants in block B. And then, just as what we did before, we compare the juiciness and tastiness of the tomatoes for each of the 2 blocks. So this way you are reducing the variability of the plants from the two different stores, okay, so that we can control for the effects of the two different plants, the two different variety of plants. In a retrospective or prospective study, subjects are sometimes paired because they are similar in ways not under study. Matching subjects in this way can reduce variation in much the same way as blocking. So for example, in the music and grades study, researchers may match each student who studies an instrument with someone of the same gender who is similar in family income but didn't study an instrument. Okay, for example, think of blocking in experiments is basically the same idea as stratifying and sampling. Okay, remember that one of our sampling techniques was the stratified random sample. And that's the one where we had homogeneous groups. We called it strata. And then you randomly, would survey within each group. Okay, so here our groups are the blocks. Recall the pet food contamination problem. Both cats and dogs were at risk. Our experiment should probably test the safety of the new food on both animals. Why shouldn't we assign a mix of cats and dogs to the two treatment groups? What would you recommend instead? So dogs and cats eat different food. They might actually respond differently to the foods, right? And that variability could obscure the results that you get. So blocking by species, cat or dog, can remove any of the extra variation. So just as you did with the dogs, where you randomly assigned them to the two treatment groups, you would do the same thing with the cats. You would randomize the cats to the two treatments. You would have the test food and then the food that's safe, but you would do that separately from the dogs. So let's write that up here. Dogs and cats might respond differently and that variability could obscure the results. So blocking by species, and we mean like cats versus dogs, could remove that extra variation. So just as we did with the dogs, my recommendation would be to randomize the cats to the two treatment groups. Same as with the dogs, where you have the test food and the safe food. And that is the end of this video. Please join me for the next one, where we're going to look at adding more factors